The history of scuba diving is closely linked with the history of scuba equipment. By the turn of the 20th century, two basic architectures for underwater breathing apparatus had been pioneered. Open-circuit surface-supplied equipment where the divers exhaled gases vented directly into the water, and closed-circuit breathing apparatus where the diver's carbon dioxide is filtered from exhaled unused oxygen, which is then recirculated, and oxygen added to make up the volume when necessary. Closed-circuit equipment was more easily adapted to scuba in the absence of reliable, portable, and economical high-pressure gas storage vessels. By the mid-20th century, high-pressure gas cylinders were available and two systems for scuba had emerged. Open-circuit scuba where the diver's exhaled breath is vented directly into the water, and closed-circuit scuba where the carbon dioxide is removed from the diver's exhaled breath which has oxygen added and is recirculated. Oxygen rebreathers are severely depth-limited due to oxygen toxicity risk, which increases with depth, and the available systems for mixed gas rebreathers were fairly bulky and designed for use with diving helmets. The first commercially practical scuba rebreather was designed and built by the diving engineer Henry Fluess in 1878, while working for Scuba Gorman in London. His self-contained breathing apparatus consisted of a rubber mask connected to a breathing bag, with an estimated 50 to 60% oxygen supplied from a copper tank and carbon dioxide scrubbed by passing it through a bundle of rope yarn soaked in a solution of caustic potash, the system giving a dive duration of up to about 3 hours. This apparatus had no way of measuring the gas composition during use. During the 1930s and all through World War II, the British, Italians and Germans developed and extensively used oxygen rebreathers to equip the first frogmen. The British adapted the Davis submerged escape apparatus and the Germans adapted the Draeger submarine escape rebreathers for their frogmen during the war. In the U.S., Major Christian J. Lambertson invented an underwater free-swimming oxygen rebreather in 1939, which was accepted by the Office of Strategic Services. In 1952 he patented a modification of his apparatus, this time named Scuba, an acronym for Self-Contained Underwater Breathing Apparatus, which became the generic English word for autonomous breathing equipment for diving, and later for the activity using the equipment. After World War II, military frogmen continued to use rebreathers since they do not make bubbles which would give away the presence of the divers. The high percentage of oxygen used by these early rebreather systems limited the depth at which they could be used due to the risk of convulsions caused by acute oxygen toxicity. Although a working demand regulator system had been invented in 1864 by Auguste Deneroux and Benoit Roucayrol, the first open-circuit scuba system developed in 1925 by Yves Leprier in France was a manually adjusted free-flow system with a low endurance, which limited its practical usefulness. In 1942, during the German occupation of France, Jacques-Yves Cousteau and Émile Gagnon designed the first successful and safe open-circuit scuba, known as the Aqua Lung. Their system combined an improved demand regulator with high-pressure air tanks. This was patented in 1945. To sell his regulator in English-speaking countries, Cousteau registered the Aqua Lung trademark, which was first licensed to the U.S. Divers Company, and in 1948 to Scuba Gorman of England. Scuba Gorman was allowed to sell in Commonwealth countries, but had difficulty in meeting the demand and the U.S. patent prevented others from making the product. The patent was circumvented by Ted Eldred of Melbourne, Australia, who developed the single-hose open-circuit scuba system, which separates the first stage and demand valve of the pressure regulator by a low-pressure hose, puts the demand valve at the diver's mouth, and releases exhaled gas through the demand valve casing. Eldred sold the first Porpoise Model CA single-hose scuba early in 1952. Early scuba sets were usually provided with a plain harness of shoulder straps and waist belt. The waist belt buckles were usually quick-release, and shoulder straps sometimes had adjustable or quick-release buckles. Many harnesses did not have a backplate, and the cylinders rested directly against the diver's back. Early scuba divers dived without a buoyancy aid. In an emergency they had to jettison their weights. In the 1960s adjustable buoyancy life jackets became available, which can be used to compensate for loss of buoyancy at depth due to compression of the neoprene wetsuit and as a life jacket that will hold an unconscious diver face upwards at the surface, and that can be quickly inflated. The first versions were inflated from a small disposable carbon dioxide cylinder, later with a small direct coupled air cylinder. A low-pressure feed from the regulator first stage to an inflation-deflation valve unit, an oral inflation valve and a dump valve lets the volume of the ABLJ be controlled as a buoyancy aid. In 1971 the stabilizer jacket was introduced by Scuba Pro. This class of buoyancy aid is known as a buoyancy control device or buoyancy compensator. A backplate and wing is an alternative configuration of Scuba harness with a buoyancy compensation bladder known as a wing, mounted behind the diver, sandwiched between the backplate and the cylinder or cylinders. Unlike stabilizer jackets, the backplate and wing is a modular system, in that it consists of separable components. This arrangement became popular with cave divers making long or deep dives, who needed to carry several extra cylinders, as it clears the front and sides of the diver for other equipment to be attached in the region where it is easily accessible. This additional equipment is usually suspended from the harness or carried in pockets on the exposure suit. Side mount is a scuba diving equipment configuration which has basic scuba sets, each comprising a single cylinder with a dedicated regulator and pressure gauge, mounted alongside the diver, clipped to the harness below the shoulders and along the hips, instead of on the back of the diver. It originated as a configuration for advanced cave diving, as it facilitates penetration of tight sections of caves, since sets can be easily removed and remounted when necessary. The configuration allows easy access to cylinder valves, and provides easy and reliable gas redundancy. These benefits for operating in confined spaces were also recognized by divers who made wreck diving penetrations. Side mount diving has grown in popularity within the technical diving community for general decompression diving, and has become a popular specialty for recreational diving. In the 1950s, the United States Navy, USN, documented enriched oxygen gas procedures for military use of what is today called nitrox, and in 1970, Morgan Wells of NOAA began instituting diving procedures for oxygen-enriched air. In 1979, NOAA published procedures for the scientific use of nitrox in the NOAA Diving Manual. In 1985, IAND, International Association of Nitrox Divers, began teaching nitrox use for recreational diving. This was considered dangerous by some, and met with heavy skepticism by the diving community. Nevertheless, in 1992 NAUI became the first existing major recreational diver training agency to sanction nitrox, and eventually, in 1996, the Professional Association of Diving Instructors, PADI, announced full educational support for nitrox. The use of a single nitrox mixture has become part of recreational diving, and multiple gas mixtures are common in technical diving to reduce overall decompression time. Technical diving is recreational scuba diving that exceeds the generally accepted recreational limits, and may expose the diver to hazards beyond those normally associated with recreational diving, and to greater risks of serious injury or death. These risks may be reduced by appropriate skills, knowledge and experience, and by using suitable equipment and procedures. The concept and term are both relatively recent advents, although divers had already been engaging in what is now commonly referred to as technical diving for decades. One reasonably widely held definition is that any dive in which at some point of the planned profile it is not physically possible or physiologically acceptable to make a direct and uninterrupted vertical ascent to surface air is a technical dive. The equipment often involves breathing gases other than air or standard nitrox mixtures, multiple gas sources, and different equipment configurations. Over time, some equipment and techniques developed for technical diving have become more widely accepted for recreational diving. Nitrogen narcosis limits the depth reachable by underwater divers when breathing nitrox mixtures. In 1924, the U.S. Navy started to investigate the possibility of using helium, and after animal experiments, human subjects breathing heliox, 20% oxygen, 80% helium, were successfully decompressed from deep dives. In 1963, saturation dives using Trimix were made during Project Genesis, and in 1979 a research team at the Duke University Medical Center Hyperbaric Laboratory started work which identified the use of Trimix to prevent the symptoms of high-pressure nervous syndrome. Cave divers started using Trimix to allow deeper dives, and it was used extensively in the 1987 Wakulla Springs project and spread to the Northeast American wreck diving community. The challenges of deeper dives and longer penetrations and the large amounts of breathing gas necessary for these dive profiles and ready availability of oxygen sensing cells beginning in the late 1980s led to a resurgence of interest in rebreathe diving. By accurately measuring the partial pressure of oxygen, it became possible to maintain and accurately monitor a breathable gas mixture in the loop at any depth. In the mid-1990s, semi-closed circuit rebreathers became available for the recreational scuba market, followed by closed-circuit rebreathers around the turn of the millennium. Rebreathers are currently manufactured for the military, technical and recreational scuba markets, but remain less popular, less reliable, and more expensive than open-circuit equipment. Scuba diving is a mode of underwater diving whereby divers use breathing equipment that is completely independent of a surface air supply. The name, Scuba, an acronym for Self-Contained Underwater Breathing Apparatus, was coined by Christian J. Lambertson in a patent submitted in 1952. Scuba divers carry their own source of breathing gas, usually compressed air, affording them greater independence and movement than surface-supplied divers, and more time underwater than free divers. Although the use of compressed air is common, a gas blend with a higher oxygen content, known as enriched air or nitrox, has become popular due to the reduced nitrogen intake during long and/or repetitive dives. Also, breathing gas diluted with helium may be used to reduce the likelihood and effects of nitrogen narcosis during deeper dives. Open-circuit scuba systems discharge the breathing gas into the environment as it is exhaled, and consist of one or more diving cylinders containing breathing gas at high pressure which is supplied to the diver through a diving regulator. They may include additional cylinders for range extension, decompression gas or emergency breathing gas. Closed-circuit or semi-closed-circuit rebreather scuba systems allow recycling of exhaled gases. The volume of gas used is reduced compared to that of open circuit, so a smaller cylinder or cylinders may be used for an equivalent dive duration. Rebreathers extend the time spent underwater compared to open circuit for the same gas consumption. They produce fewer bubbles and less noise than open-circuit scuba, which makes them attractive to covert military divers to avoid detection, scientific divers to avoid disturbing marine animals, and media divers to avoid bubble interference. Scuba diving may be done recreationally or professionally in a number of applications, including scientific, military and public safety roles, but most commercial diving uses surface-supplied diving equipment when this is practicable. Scuba divers engaged in armed forces covert operations may be referred to as frogmen, combat divers or attack swimmers. A scuba diver primarily moves underwater by using fins attached to the feet, but external propulsion can be provided by a diver propulsion vehicle, or a sled pulled from the surface. Other equipment needed for scuba diving includes a mask to improve underwater vision, exposure protection by means of a diving suit, ballast weights to overcome excess buoyancy, equipment to control buoyancy, and equipment related to the specific circumstances and purpose of the dive, which may include a snorkel when swimming on the surface, a cutting tool to manage entanglement, lights, a dive computer to monitor decompression status, and signaling devices. Scuba divers are trained in the procedures and skills appropriate to their level of certification by diving instructors affiliated to the diver certification organizations which issue these certifications. These include standard operating procedures for using the equipment and dealing with the general hazards of the underwater environment, and emergency procedures for self-help and assistance of a similarly equipped diver experiencing problems. A minimum level of fitness and health is required by most training organizations, but a higher level of fitness may be appropriate for some applications. The safety of underwater diving depends on 4 factors: the environment, the equipment, behavior of the individual diver, and performance of the dive team. The underwater environment can impose severe physical and psychological stress on a diver, and is mostly beyond the diver's control. Scuba equipment allows the diver to operate underwater for limited periods, and the reliable function of some of the equipment is critical to even short-term survival. Other equipment allows the diver to operate in relative comfort and efficiency. The performance of the individual diver depends on learned skills, many of which are not intuitive, and the performance of the team depends on communication and common goals. There is a large range of hazards to which the diver may be exposed. These each have associated consequences and risks, which should be taken into account during dive planning. Where risks are marginally acceptable, it may be possible to mitigate the consequences by setting contingency and emergency plans in place, so that damage can be minimized where reasonably practicable. The acceptable level of risk varies depending on legislation, codes of practice, and personal choice, with recreational divers having a greater freedom of choice. The risk of dying during recreational, scientific, or commercial diving is small, and on scuba, Deaths are usually associated with poor gas management, poor buoyancy control, equipment misuse, entrapment, rough water conditions, and pre-existing health problems. Some fatalities are inevitable and caused by unforeseeable situations escalating out of control, but the majority of diving fatalities can be attributed to human error on the part of the victim. Equipment failure is rare in open-circuit scuba. According to death certificates, over 80% of the deaths were ultimately attributed to drowning, but other factors usually combine to incapacitate the diver in a sequence of events culminating in drowning, which is more a consequence of the medium in which the accidents occurred than the actual accident. Scuba divers should not drown unless there are other contributory factors, as they carry a supply of breathing gas and equipment designed to provide the gas in demand. Drowning occurs as a consequence of preceding problems such as unmanageable stress, cardiac disease, pulmonary barotrauma, unconsciousness from any cause, water aspiration, trauma, environmental hazards, equipment difficulties, inappropriate response to an emergency, or failure to manage the gas supply, and often obscures the real cause of death. Air embolism is also frequently cited as a cause of death, and it, too, is the consequence of other factors leading to an uncontrolled and badly managed ascent, possibly aggravated by medical conditions. About a quarter of diving fatalities are associated with cardiac events, mostly in older divers. There is a fairly large body of data on diving fatalities, but in many cases the data is poor due to the standard of investigation and reporting. This hinders research that could improve diver safety. Fatality rates are comparable with jogging, 13 deaths per 100,000 persons per year, and are within the range where reduction is desirable by Health and Safety Executive (HSE) criteria. The most frequent root cause for diving fatalities is running out of or low on gas. Other factors cited include buoyancy control, entanglement or entrapment, rough water, equipment misuse or problems, and emergency ascent. The most common injuries and causes of death were drowning or asphyxia due to inhalation of water, air embolism, and cardiac events. The risk of cardiac arrest is greater for older divers, and greater for men than women, although the risks are equal by age 65. Several plausible opinions have been put forward but have not yet been empirically validated. Suggested contributing factors included inexperience, infrequent diving, inadequate supervision, insufficient preventive briefings, buddy separation, and dive conditions beyond the diver's training, experience, or physical capacity. Decompression sickness and arterial gas embolism in recreational diving have been associated with specific demographic, environmental, and diving behavioral factors. A statistical study published in 2005 tested potential risk factors: age, asthma, body mass index, gender, smoking, cardiovascular disease, diabetes, previous decompression illness, years since certification, number of dives in the previous year, number of consecutive diving days, number of dives in a repetitive series, depth of the previous dive, use of nitrox as breathing gas, and use of a dry suit. No significant associations with risk of decompression sickness or arterial gas embolism were found for asthma, body mass index, cardiovascular disease, diabetes, or smoking. Greater dive depth, previous decompression illness, number of consecutive days diving, and male biological gender were associated with higher risk for decompression sickness and arterial gas embolism. The use of dry suits and nitrox breathing gas, greater frequency of diving in the previous year, greater age, and more years since certification were associated with lower risk, possibly as indicators of more extensive training and experience. Risk management has three major aspects besides equipment and training: risk assessment, emergency planning, and insurance cover. The risk assessment for a dive is primarily a planning activity, and may range in formality from a part of the pre-dive buddy check for recreational divers, to a safety file with professional risk assessment and detailed emergency plans for professional diving projects. Some form of pre-dive briefing is customary with organized recreational dives, and this generally includes a recitation by the dive master of the known and predicted hazards, the risk associated with the significant ones, and the procedures to be followed in case of the reasonably foreseeable emergencies associated with them. Insurance cover for diving accidents may not be included in standard policies. There are a few organizations that focus specifically on diver safety and insurance cover, such as the International Divers Alert Network.